Assalamualaikum warahmatullahi taala wabarakatuh and good morning. I'm Dr. Sabah Bau from the Physics Section, Pusat Pengajian Pendidikan Jarak Jauh, University Science Malaysia. This is course JIF 318 Quantum Mechanics. We are in Chapter 5 Linear Algebra, Matrices and Direct Notation. In this segment, Unit 5.6, we'll discuss the metric formulation of linear operators. The objective of this lesson is basically for you to be able to describe the formalism of treating finite dimensional vectors for which linear operators are represented by matrices. Recall that the set of wave functions psi in terms of x can be treated as an infinite dimensional vector space. Okay, remember in some of the previous segment we have discussed the vector space. That means if we have three vectors, for example, in three-dimensional world, we can plot it in a graph of vector r in terms of the unit vectors x, y, z, and we have three dots in the plot of r against I, where I is the number of dimensions. So if we have n dimension, there's many dimensions, we have many dots in the graph, then the graph is actually can be represented by function, okay, as a function, can be treated as a function. So a set of wave functions psi can be treated as an infinite dimensional vector space. However, we will often be interested in finite dimensional vector spaces, for example, in the study of angular momentum. So in real life, and we will always have finite dimensional vector spaces. Suppose that a particle has a total angular momentum j equal to half, so that the possible mj states are negative half and positive half. So if j equal to half, then we have two possible states, negative half and positive half. That's what we call as finite dimension. We can represent these two states as column vectors. Okay, we can represent this as column vectors. The first one is the column matrix lah. Okay, 1, 0 can represent the mj equal to positive half state, and 0, 1 can represent the mj equal to negative half state. This is an example how we represent the two states using column vectors. In fact, this is already a matrix. Okay, the dimension of the vector space is just the number of entries in the column. So basically, the dimension, we say that n dimension. That means if you have two dimension, like this present example, we have two entries in the column. If we have three, that means we have three entries. If we have n dimension system, then we have n number of entries in the column. So the question is, how is a linear operator represented using this formulation? That means using this column and rows and whatever, or in other words, in matrix. So a column vector with n entries can be treated as n plus 1 matrix. N plus 1, that means we have n rows and 1 column. Okay, hence multiplying n multiplied by n matrix by an n multiplied by 1 column vector yields another n multiplied by 1 column vector. Here you have n multiplied by n, here you have n multiplied by 1, here you have n multiplied by 1. That means in this case, for example, we have three-dimensional system. So you have 3 by 3 matrix multiplied by 3 by 1 matrix equal to 3 by 1 matrix. So this is already in matrix form. Okay, so if we have this expression, basically we can have three solution or three-dimensional system here. Since matrix multiplication is not commutative, it will not be true that any two operators will commute. So for example, like here n by n and n by 1 is not necessarily commutative. What do you mean commutative? That means if let A, we have this matrix 1, 2, 3, 4, and B 5, 6, 7, 8. AB is not equal to BA. We can prove this. For example, if AB equals to this, then we have this metric uh, expression, okay, or operation, okay. So we have this, okay. While BA, we have another matrix which is not equal to AB. So we have this AB not equal to BA. That's why the above said, the sentence in the above said that matrix multiplication is not commutative. If they are commutative, then AB must be equal to BA. So in this, you can say that matrix multiplication is not commutative. Okay. We can also find the eigenvalues and eigenvectors of an operator represented by a matrix. That means you can represent the what we call the eigenvalues and eigenvectors equation as we have come across in the previous segments as a matrix. Suppose we have a matrix A multiplying a column vector X, and assume that one of the eigenvalues is C. So we have this expression, even though in the previous what do you call it, segment, we have wave vector or wave function, but since wave function is equivalent to space vector, we can also have the expression as representing this type. The form looks similar, okay, except that now the wave function is replaced with a space vector here X. So C an eigenvector, so we can multiply with this no, X is an eigenvector, we multiply with an arbitrary constant, so we can say that this is an eigenvalue, just like in the Schrodinger equation case, okay. Except here we say that it is eigenvector rather than eigenfunction. Anyway, vector, space vector and function has some relationship. So A here is the matrix, okay. In Schrodinger equation, usually that place is used by an operator, okay. That's why we have this sentence here. We can also find eigenvalues and eigenvectors of an operator. So the operator is represented by a matrix. This can be written, that means the AX equal to CX can be written in terms of identity matrix I. So to play around with matrix or matrices, we can insert I here, a matrix. You see? It is called identity matrix I. What is identity matrix? A matrix with values of 1 in the diagonal here and the rest are zeros, okay? It can be 3 by 3, can be 4 by 4, n by n here, okay? So the expression can be rewritten as matrix A multiplied by eigenvector X equal to eigenvalue C multiplied by unit vector identity matrix I multiplied by eigenvector X. So we rearrange, we can get A minus Ci, the whole thing multiplied by the eigenvector X equal to 0. So let's say we have three-dimensional system. So basically the vectors x1, x2, x3, while the matrix here is this. You can see that the diagonal is subtracted by C, okay, because we have multiplied C to the identity matrix, so that we have uh, the matrix here is equal to C all along the diagonal, while the rest is 0. So when we multiply out, so the diagonal we have minus C. So when we subtract this A, okay. For a non-zero solution, the determinant of A minus Ci must be 0. Okay. If we want to have this relation non-zero solution, that means for the vectors here to be non-zero, so here should be 0, the determinant. This is what we call as determinant in metric, multiplied by the variable here equals to 0. So of course, if this is not equal to 0, then the first metric should be equal to 0. That's what we call as determinant. That means A 1 1 minus C and so on and so forth equal to 0. Thus there will be always be n complex values of C for which determinant is 0, corresponding to n complex eigenvalues. So this is just 3 by 3, but if you have n complex eigenvalues, then we have n complex values for C. Okay. So in conclusion, linear operators of finite dimensional vectors may be represented by matrices. Okay. Theoretically, it can go to n dimensions. Okay. Thank you very much for your attention.